Kicking us off will be Rachel Street with the TOM Toolkit. Please take it away, Rachel.
Hello, everybody, and thanks very much for giving me this opportunity to present. Our team's work focuses on using software to meet the challenges associated with coordinating astronomical observing programs, and I'd like to tell you about some of the tools that we've developed for this purpose. But before I go on, I want to give all credit to our development team, which is a collaborative effort between the software development team at Las Cumbres Observatory and our in-house scientists. Let me start by quickly recapping the scientific motivation for our software tools. As you know, modern astrophysics has entered an era where we have a wealth of targets of all kinds. A wide range of surveys are in operation at all wavelengths and messengers, generating vast catalogues of discoveries and data products in the petabyte range. Advances in data processing mean that many surveys also issue alerts of new discoveries in real time, and the rate of alerts is expected to increase by an order of magnitude over the next few years. Improvements in survey technologies have, of course, opened up new areas of parameter space, and astrophysics has discovered new phenomena such as kilinovae and confirmed the existence of phenomena that were theoretically predicted but technologically hard to detect, such as gravitational waves. Massive object catalogues, including extensive time series data, are enabling us to understand the evolution of different categories of objects by studying their population distributions. This wealth of discoveries means that researchers from all branches of astrophysics are facing the same challenges of searching this huge haystack of data for the needle of the targets that they are particularly interested in, and collating all relevant data on those targets from a wide range of sources. If the targets are static or relatively slow to change, this can be a very labor-intensive task. But for those targets which change or move rapidly, the challenges are compounded by the need to act quickly to ensure that all necessary data is acquired while the target can still be observed. Furthermore, for many areas of science, the survey discovery data alone isn't enough, and additional follow-up observations are needed in order to characterize each target. This was highlighted in 2016 by Najita et al. They conducted a study of the follow-up instrumentation that will be necessary to characterize a range of different targets detected by the Vera Rubin Observatory's legacy survey of space and time. As you can see from this table, almost all branches of astrophysics will require additional data from multiple different facilities in order to complete their science goals. Now, other speakers have done a great job of describing the data archive and alert broker facilities that are designed to provide astronomers with access to the survey discovery data. But once those have done their job, what's the next step to achieving our science goals from those data products? Even though any one astronomer or team may be interested in a specific subset of survey discoveries, they still have a lot to keep track of. There's a constant stream of alerts and new discoveries to be evaluated, often within hours if your science happens to focus on transient phenomena. Some of those targets will need further observation, and those targets must be identified, prioritized, and an appropriate observing strategy decided on. This means that researchers have to constantly juggle lots of different targets, all in different phases of evolution, some newly discovered and some the subject of long-term study. Quite often, teams have to manage observations involving a number of different telescopes and instruments in order to characterize a single target. And although the resulting data products are smaller than those for a survey, there is still more to keep track of than is feasible for even a team of human beings. Just the follow-up program alone can involve thousands of observations and terabytes of data. And not least, you need to coordinate the human team behind your project. And these days they are often geographically distributed. Everybody needs easy access to the project's data. Software tools can be an extremely powerful way to help teams to manage these challenges in a sustainable way and to enable them to achieve their scientific goals without being overwhelmed. Database-driven systems designed to manage astronomical projects and their associated data can act as a bridge, interfacing with data archives and other astronomical services to enable researchers to more easily accomplish their science. As a general category of software, I'll refer to these as target and observation managers, or TOM systems, and a number of research teams have independently developed such systems for a wide range of different science, from the Fritz system developed by ZTF and the Supernova Exchange, to the NEO exchange system for studies of near-Earth asteroids. Although a number of such systems have been developed by various major projects, they are not trivial to build from scratch and require substantial software development and database expertise that is not universally available to the whole community. Nevertheless, when you look closely at some of the systems in use, it's striking how many common features they share, despite having been designed for quite different science goals. This indicated to us that it would be valuable to build an open source package designed to make it easy for any astronomer to build a TOM system and customize it for their science, without having to reinvent the wheel or become an expert in database design. The TOM Toolkit package is designed for this purpose. Our approach is to have the core package developed and supported by LCO's professional software engineers, working in close collaboration with astronomers both at LCO and in the wider community. We aim to provide a base toolkit that supports the commonly used functions and interfaces to avoid users having to reinvent the wheel, but we also designed it so that even a novice developer would be able to customize it to their own workflow. The package is written in Python and based around the Django web framework so that the system can be accessed simply from a browser without the users needing to install some local application. At the heart of a TOM system is a database which is designed to store data on astronomical targets. The TOM includes a browser-based user interface, and the base toolkit includes many of the displays and user interface tools that are commonly needed by astronomical projects. Naturally, this includes the interfaces needed for astronomy, but it also includes the underlying project infrastructure, such as managing user accounts. The package includes a fully featured TOM system out of the box, with a setup script that talks you through the setup process. So it's quick and easy to have your own TOM system up and running within minutes. The database is organized around the user's set of targets of interest and all associated data. While the default database is set up for basic parameters such as name, coordinates, etc., this parameter set is designed to be extended by the user to include information that is specific to the science in question, such as modeling parameters, for example. The TOM also supports the constructions of lists of targets and includes essential search functionality and interactive plotting tools which assist the user's workflow. But the design of these pages is highly customizable. As you can see here in this example of a target page that has been customized for supernovae follow-up with the SNEX-2 system built by Jamie Burke, Craig Pellegrino, and Andy Howell. It's particularly important for the toolkit to provide interfaces to a wide range of external services in astronomy, as this allows the user to quickly and easily collate data and alerts on their targets of interest, evaluate the combined information, and make decisions about their scientific strategy for each target. Thanks to the powerful programmatic interfaces provided by many alert brokers and data archives, it's increasingly possible for researchers to automatically receive notifications of new discoveries of interest and to gather the information they need via software. This also speeds up the workflow, meaning that researchers can respond more effectively to new discoveries, particularly transient phenomena that require a rapid response. Rather than have every research team reinvent the wheel and produce many versions of effectively the same interface software, the toolkit provides a set of built-in modules to handle these interactions with a range of public alert broker facilities. We also provide interfaces to a number of data archives, and we are keen to partner with a wide range of other archives to expand this list of supported facilities. The toolkit provides the means for users to upload their own data products to their TOM as well. These can be raw or processed data associated with observation requests, or standalone data products, such as those produced by user-developed analysis software. The toolkit includes tools for uploading data in many common formats, including time series data, and the JSON-based ingest is very flexible. Users are encouraged to adapt it to upload data in whatever format is most suitable for their science. The toolkit also provides built-in tools for data visualization to allow users to inspect their data directly within their browser. These are very interactive and include image display tools as well as interactive plots, which can also be customized. One of the most powerful capabilities that a TOM offers is the ability to submit requests for additional observations directly to telescope facilities. This streamlines the follow-up of all kinds of astronomical targets and significantly reduces the workload of managing observing programs, especially when multiple telescopes are needed. A range of telescope facilities now offer such a service, and the number is increasing all the time. For this reason, the toolkit includes a set of built-in modules and interfaces that allows users to submit observing requests, monitor their execution, and harvest the resulting data products from telescope archives. Once again, we are keen to partner with a range of observing facilities to make more instruments available this way. In addition to the browser-based user interface that comes with the toolkit, I want to emphasize that most of its functionality can also be accessed programmatically. All modules include APIs that are designed to allow the functions to be called directly from external user-developed software. There are a range of scientific motivations to do this. For example, choosing which targets are of interest to a user's scientific research and prioritizing those targets is obviously something that is highly science-specific and has to be user-developed. In many cases, selection algorithms can be written, which has the advantage of very clearly quantifiable selection biases. The toolkit provides APIs to enable this software to interface directly with the TOM. Likewise, data reduction pipelines can also interface directly with the TOM, for example, to streamline the upload of reduced data products as soon as they're available. This is a crucial element in enabling fully robotic project management, which not only reduces the workload on researchers, but also makes the project more efficient and able to react more quickly, which is particularly important for transient science. The toolkit has a number of features that offer project teams flexibility in how they run their program. The first is access control permissions. By default, any TOM user can access anything in the TOM, but we recognize that not all projects can work that way. Users can then indicate which groups should have access to which targets by selecting appropriate checkboxes, as you can see from this section of the Target Create view. Similar access controls can also be applied to records of observations and to data products at the discretion of the administrator. Another feature that the TOM offers is support for predefined cadence strategies. It's often the case that astronomers can define their observing strategy in advance, even if they don't know exactly what their targets will be. For instance, when a supernova is detected, an observing team who have applied for time on a given telescope know that they're going to be taking time series imaging in multiple filters every few days, and likewise spectra. This may need to continue for several months. So a common situation is that a team nominates a suitable target and requests a set of observations. But weather or another factor might conspire to interrupt the time series. With perhaps hundreds of targets to monitor at any given time, keeping track of these observations can become quite a high workload on the human team. So the toolkit supports observing strategies, which enable the TOM to carry out predefined observations for you. Users can write a small Python function which tells the TOM what to do under certain circumstances. The toolkit includes an example that will automatically resume an expired observing request in the event that no observations were obtained within the given time frame. Our team has consciously sought to partner with a number of other service providers in astronomy from the outset of the project, and we're delighted that a number of partners have contributed plugin modules that enable users to interact with a range of alert brokers and telescope facilities. So a big thank you to all our partners. We would very much welcome the opportunity to work with additional astronomical services and support a wider range of functionality, so please get in touch if you're interested. We also provide a range of extension modules for the toolkit. In most cases, these include functionality which we feel is widely beneficial, but which sometimes makes use of external packages, which causes a little bit of extra complexity when a TOM is deployed to a public server. To ensure that the base toolkit is kept as simple as possible to use, these packages are optional. The extension modules cover a wide range of additional features, from more interactive plotting tools to an interface for a developing platform for Multimessenger alerts. But there is one module that I would particularly like to highlight. Multimessenger alerts present some distinct follow-up challenges, as the initial discovery data is often not well localized. And the first task for research teams is to pinpoint the specific source of the signal, and to do so very quickly before the event becomes undetectable. By definition, they must collate information from a number of different sources in a meaningful way and streamline the evaluation process as much as possible. And it's often the case that they will have a number of candidate targets associated with the same event. Our team have been collaborating with Andy Howell to develop this new user interface. It's designed to help follow-up astronomers collaborate to create prioritized lists of candidate targets, coordinate observing requests to a variety of facilities, receive the resulting data, and then reevaluate and eliminate non-viable candidates. At all stages, it keeps collaborators informed of all findings and activities until the source of the event has been determined. We are working to have this available as soon as possible, and certainly by the 04 gravitational wave detector run. These new, more responsive JavaScript tools have been built using the Vue JavaScript framework. This has allowed our team to implement a number of reactive user interface elements, such as candidate tables that can be sorted or searched on with a single click. The framework is integrated with the toolkit in such a way that it will be possible to extend the number of reactive tools we have available, so that all users will be able to take advantage of the smoother workflow that they offer. We also hope to extend the TOM Super Events module in future to support coordination between teams of observers. When a high priority event is discovered, it is often the case that many teams will attempt to follow it, and services such as the Treasure Map system are designed to make this process more efficient by helping observers to coordinate their efforts. More and more observing facilities are developing programmatically accessible interfaces, and this has been a particular priority for the Rubin Observatory, to increase our capability to efficiently respond to alert streams. So expanding the number of facilities that the toolkit supports is naturally an ongoing priority for us. This is highly complementary to another software project by the Las Cumbres teams, the Observatory Control System. For any telescope operator, the control system for the facility is obviously critical, but time-consuming and expensive to develop in-house. This is something that at Las Cumbres had to do when we developed our network. So we are now repackaging our control software into a standalone software package that can be used independently by other facilities. A key aspect of this system is that all core functions can be performed by API, meaning that they can be easily incorporated into web interfaces and software to support different workloads. And this includes integrating the facility with the TOM Toolkit if desired. The package includes a browser-based observation portal where users can submit observation requests and monitor their progress. This module stores the observation schedule and provides APIs for a telescope site to access that schedule and update the status of each observation. The APIs mean that the observing programs can operate robotically, enabling more reactive science. The scheduler generates an observing schedule for the telescope based on the request submitted, and feeds this information back to the portal. This system is based on LCO's own algorithm, which is highly adaptive, meaning that it generates a new schedule whenever there are changes to the requested observations or the state of the telescope. The scheduler supports several modes of observations, including normal requests that take place within a user-specified window, and time-critical requests that receive higher priority to ensure that they take place at a specified time, such as for a planetary transit, for example. The system also supports rapid response requests that need to be executed as soon as possible. Provided the target is visible from the telescope, these requests will begin within 15 minutes. The package includes a data archive system designed to store data products from the observatory and make them available to users via a browser-based interface, which also offers API functions. This provides fast and reliable access to the data, which is again well suited for reactive science. Every observatory must obtain routine calibration data for all of its active instruments, and Las Cumbres is no different. Since this is in reality a specialized type of observing program, when it came time to overhaul that element of our software, we chose to use the TOM Toolkit to manage calibrations across the network and to provide our operations team with suitable monitoring tools. This is a screenshot of Calibration TOM's display of spectroscopic standard star observations in progress for our different telescope facilities. Our teleops team are able to start, stop, and pause observations for specific standards, but otherwise the TOM will continue to manage these automatically. We are currently working to include photometric calibrations as well. I'd like to wrap up by highlighting the user support that our team offers for anyone developing a TOM system. The package has extensive online documentation, and we also provide a set of training materials that work through installing and customizing your own system. We also run a developers forum as a virtual meeting and a Slack channel where research teams can directly contact our software engineers to ask for advice on TOM development. So thank you for your attention, and if you have any questions, I will be happy to answer them.
Perhaps while we wait, I can ask one of my own. Very impressive. So one of the, broadening this to radio interferometry and millimeter interferometry, scheduling an interferometer has additional complexities in UV coverage, and there's an opportunity for optimization there when considering multiple requests. Would you envision this incorporating something like that, or would you leave that up to the observatory or the users with that Python script you mentioned?
That's a really great question. And yes, scheduling multiple facilities has been something that the team has talked about for some time, but it involves a lot of various complexities if you are talking about facilities that are not under central control. So the advantage with the scheduler that I just showed you is that it's designed to work with all facilities that are under a single institution's control. So for an interferometer, although it hasn't been applied in that context, one could imagine that it could be adapted for that purpose, because an interferometer, those facilities are all under an individual institution's control. The real complexity happens when you start trying to schedule observations when you involve multiple observatories, all of which have their own user bases and all of which have their own policies. And that is an outstanding challenge that we have not yet investigated.
Thank you. Okay, so we have a few questions here online. The first is from William O'Mallane. The observatory control mentioned looks a little bit more like an observation scheduling system. Does it contain instrument and telescope control modules?
So it incorporates all of the different elements that one needs to operate an observatory, but obviously every observatory has its own instrumentation. So that is handled as a configuration which the user is able to set in advance and would obviously tailor to their own instrumentation.
Great. Next up, Stephen Gwynn. How do you set priorities between fields? And a second question, is my asteroid more important than your supernova?
The age-old question. The TOM system itself and the scheduler don't set any priorities. That's important to know. So the priority of one observing program relative to another on any given facility is up to the time allocation committee that awards time on that facility. So we assume in advance that a facility has allocated time according to whatever protocol it follows, and the TAC has awarded some kind of priority ranking to the different proposals that are in operation. And that proposal priority is part of the configuration that when the TOM system submits observation requests to that facility knows in advance what the priority of a given proposal actually is relative to everything else that it's doing. So it's on the telescope operator has complete control over what programs it prioritizes relative to another.
And then David Buckley asks, I suppose he was in the room earlier, but is no longer, if I'm correct. Would you like to comment on the synergy between TOMS and Aeon? Can the latter work independently of TOMS?
Right. So TOMS becoming compatible with the TOM Toolkit is one of the two avenues, optional, that a facility can take if it wishes to become compatible with the Aeon multi-facility network. But there are other options. So if a facility has, for example, its own API systems and its own control systems existing already, then it's entirely welcome to use those. All it really needs to do to be Aeon compatible is provide APIs that can be programmatically addressed and run at least part of its schedule in a queue scheduled operation. And that makes it very, very flexible for time domain observations. But compatibility with the TOM Toolkit is one of those options.
Great. Ryan Timmons asks, does the OCS have any support for space-based telescopes or instruments?
Oh, that's interesting. So the Open Control System was primarily aimed at ground-based facilities. But one thing that is becoming more and more available now is there are APIs being developed for space mission facilities. In particular, the Swift telescope springs to mind. And we are in the process of speccing a module for the toolkit that we would like to be able to submit observation requests directly to Swift to make advantage of that API. So that's definitely in the future development category.
Great, thank you. Any last questions for Rachel? I don't see any typing, so let's have a round of applause for Rachel, please.
Thank you all.
Thank you very much indeed.